Swayam Prabha. Digital India. Educated India.
So, we continue with whatever we left out yesterday. Just I throw open a thought. We need to take care of a lot of things while paging is enabled. Should I take care of something more, which is architecture specific? While enabling paging. And with that we will end paging. So, I will give you a clue, pipelining. With respect to pipelining, what will happen?
The fetch operand stage. The fetch operand stage will vary depending on whether the page is available.
Exactly, beautiful. See, now that's so I have fetch instruction stage, I have decode, fetch data, execute, store result. Let us take this common thing. Where will the pipelining get enabled? When will the paging get enabled? Which stage will the paging get enabled? Huh? See, there is a bit in a register, and that bit, when it is set to 1, it will go and enable paging. So, when will paging get enabled? Huh? Decoder. Store the result, because this pattern has to go and sit in the register. After that only that bit gets enabled, and then so by the time you do, several things can happen in this pipeline. And just for the fun of it, if I am going to say that I will plan in such a way that the instruction that enables paging, the next instruction is exactly in some other page somewhere, so that, but I will map it properly. Are you able to get this? Suppose I could map it properly. So just to make fun of the architecture, what I can do is say this is the instruction that enables paging, and there is some other page somewhere. So the next instruction I want it to execute would be, say, here, somewhere here. Okay, somewhere here. So the moment I enable paging, the next instruction to be executed will be fetched from here, should be fetched from here, right? Suppose I write a program like this, I can write a program. Then if your processor is not working correctly according to this, will your processor actually work correctly? No, because by the time you store this result, this instruction, this 4 of these instructions could eventually be populating this pipeline, right? By the time you realize that this instruction is enabling paging, there will be 4 other instructions that follows could have come and populated this pipeline, and they need not necessarily be the instructions that should be executed after it. Number 1. Number 2, suppose they are fetching some data, assume it's a load store instruction, they may be actually the instruction, assuming even that I am identically mapping the page which enables paging. Let these 4 be the instructions, they have come here, but it need not necessarily be that the data fetched by this instruction and this instruction be exactly the same. They can now, because of paging, it can fetch from some other location. Are you able to get this? Right? And in the act of it getting fetching this, it might also lead to a page fault. Right? So all that I have done in terms of, without realizing that the forward instruction is enabling paging, all that I have done in the past have to be completely undone. So the pipeline has to be flushed while I enable paging. Right? Pipeline has to be flushed. It is not just flushing the pipeline. Please understand, I should also go and reload my PC, my program counter, so that after this is over, the next virtual address is given, and then it is, no, I have to subtract it by the number of instructions that I have fetched. Okay, right? And interestingly, there could be a jump instruction after this, a conditional jump, and that would have predicted correctly saying taken, and that would have gone and adjusted this PC. Some other instruction could have also come. So many complications can happen by the time this fellow realizes that paging is. Are you able to appreciate, understand what I am trying to say? Okay. So that is why. So the architecture. So the way of handling this is, the moment I say enable paging or moment I say enable segmentation, for example, both can have the same issues. I can basically now go and say that flush all the pipelines. So I will make the architecture go and flush the pipeline. Okay. 1 minute. Otherwise, what we should do, the compiler should do something to flush the pipeline. That is what, if when we enable paging, then just after that there will be one jump, next label and next label colon. Just a statement. So this is a unconditional jump, and the moment I put a jump, there are certain architectures which will flush the pipeline. Right? If there are no prediction, the moment I see a jump, I flush the pipeline. So while the jump can certainly execute, this is PC relative jumping. So this jump will execute irrespective of whether you have enabled paging or not. And even if it executes, it will just go to the next label and it will not do anything. And after that, obviously we can, paging gets anyway enabled. Okay. So this is something very interesting. Now, the way compiler could have handled this, that after enabling paging it could put several no-ops. But if I am going to have such a compilation, then as my architecture changes, the compiler also has to become different, right? So yes, as we go on improving the performance of the processor, there are a lot of things that come as a baggage to keep consistency with the execution of the program. These are all very, very simple examples which basically tells you that as your processor becomes complex, as you go on increasing your pipeline and all these things, what is it that we have to take care? Where will we fail? Right? So if you look at the entire processor design process, the 75% of the time is spent on what we call as verification. Whether after doing a change, if all my original programs will work properly or not, right? So the entire designing a processor, only 25% is actual design, the remaining 75% is actually verification. Okay, and this is very, very crucial. Verification or validation, you can call a lot of things, or testing. These are all not really synonymous, but we can use it at least now. Okay, so I am just giving you case studies relating to what the OS or the compiler needs, and what we basically land up complicating the architecture, and how careful we need to be. Okay. And you will agree with me that this is a very, very simple, obvious fact, correct? But it didn't strike us, right? So that's why you should start. Your imagination should be imagination level. I don't know whether you call it analytical ability or this thing. I think an imagination ability should be much stronger if you want to be a computer architect. That's why the word architecture has come, right? Architecture needs more imagination. So that is very, very important. So you should start imagining. Then only you will start. So when the world thinks in one way, you should start thinking in some other way, right? And this one very interesting thing. 1, 3, 5, 7, 9, 11, 13, 15, 17, 19. What is next? Huh? Huh? Could be anything. Can you tell me? Yeah, could be anything. I can.
20, 21.
So, can you give me a reasonable argument?
Okay, for 21, like.
21, okay, anybody will say. Like I will say.
If I take multiples of 19.
You have sat through Kharagpur class?
Maybe.
Yeah. So you know that. Somebody has taught you that. Can you tell me 31 why? Don't. Can you tell me 31? Why 31? Because if I look at, I am constructing all these numbers with only odd digits, and the next odd digit after 19 is 31. Correct? I can say 20, that fellow said 20. Just take 19 table, right? 19 ones are 90, 19 twos are 38, like that you come. 19 tens are 190, 19 11 is 209, right? Just do mod 10, you will get 1, 3, 5, 7, 9, 11, 19, and then you will get 20. So after this I could have 20. But you can actually fit functions to say that I could have anything after this. I could have even minus 5, minus 7, anything. Right? They are very interesting. So this is what we term as something out of the box thinking. So let us go to the next part. So we had disk where we had the virtual address space, and then we had the RAM where we had the physical address space. Now this is a bus to which this RAM is connected. This RAM is connected using something called a memory controller. This memory controller is basically an hardware, and then here sits the CPU, here sits your printer, there will be a printer controller, here sits your disk, and you have a disk controller, and this is your hard disk. Here is your graphics card, and then here sits your monitor, right? Then here there are peripheral interface like PCI Express. You can put anything, your sound card, whatever you want to put. So this is a basic system. Right? Now, when the CPU wants to access RAM, it actually goes through this. This is a common bus. Sometimes this is also called as FSB, front side bus. Right? So when the CPU wants to access RAM, it goes through this bus. Right? It accesses RAM and so whenever it has to go through this bus, again it will wait for, so essentially this disk is here, okay. Essentially it again waits for getting that bus, so there is a latency tau, plus then there is a memory access time. Memory access is read or write, so I will call it as memory access time, and it reads. So suppose this tau plus m is the total time required for reading some 1 byte from the memory. So tau is the latency. The same thing we have talked, when RAM wants to talk to disk, it has to actually, when I want to move from RAM to disk, I have to wait for the bus and then. Now also understand that the very few peripherals talk directly to the CPU. The way by which peripheral actually talks to the memory is through, talks to the CPU is through memory. Okay, very few peripheral talks directly with the CPU. In the sense, can you tell me one peripheral which will directly has to talk to the CPU? And in which way does it talk? Keyboard, for example, right, has to talk to the peripheral, right? Keyboard has to talk to the CPU. Why? Control C, you press, it has to stop. No? When a program goes on an infinite loop, you go and press Control C, it has to stop. So keyboard talks to the CPU through what we call as the interrupt mechanism. So that's why you have several other interrupts, right? And sometimes it is a non-maskable interrupt. I can't stop that interrupt. So if I press Control C, irrespective of what is happening, even great program is running, VVVIP program is running, it will go and stop. Okay, right? But many peripherals will not transfer data directly from disk to the from the peripheral to the CPU. It will write into the memory and then you take it from the memory. Right? And 1 minute, when just a minute, when there is a data transfer between the peripheral and the RAM, the CPU need not be involved. Right? Why should the CPU just keep watching what is going on? It will say, yeah, do that, and it can basically start doing some processing. Okay, right? So this is called DMA, direct memory access. So there will be something called a DMA controller in this bus, and when a peripheral, when the CPU wants some data, it will tell the disk controller, transfer this much amount of data, and then it will start doing its own activity, some other activity, and then the disk controller will transfer that data to some location in the RAM. Okay, and it will bypass the CPU. Right? CPU will just say, I need this data. Disk controller and RAM will talk to each other, and the data transfer will be done. And similarly, I want to write back to the disk. I'll tell the RAM, I'll tell again the DMA saying, this amount of data from RAM has to go to disk, and then this, as a CPU, I don't get involved further, and that transfer happens. That's why we call it as disk direct memory access. Okay, we will understand more about it when we go into the IO part. That's the last part of this course, right? But as of now, this is, we need to understand that if the CPU wants to access RAM, like how RAM when it wants to access the disk, right? It has to wait, it has to request the bus, it has to wait for some latency, tau time, and then it gets control over the bus, and then it goes and access. And so the total time involved is not just access time, but is some tau plus m time. And so that's, I'll come back to your question, Chidan. The same argument, so suppose I want to read k bytes from the memory. For example, x86 is a byte addressable memory. So suppose I want to read k bytes, then it becomes k into tau plus m. I access one byte, give off the bus, again request for the bus, then access next byte. Instead of doing that, whenever I access one byte, I don't just bring that byte alone, I bring a block of data. The word block is used here. Block was used even in the one block was for me one page in the case of paging. Here also I bring one block of data from the memory. So then what happens is, let that block be k bytes, then the total time involved now will become tau plus k into m rather than k into tau plus m. So this is now become tau plus k into m. So I reduce, I actually improve the performance by several folds, because my tau, which is reasonably significantly large amount, is not getting multiplied by k. And this type of a transfer is very good for me because it will be beneficial for me because of what? Locality of reference. So I have both spatial and temporal locality. So because of locality of reference, this particular block transfer is going to be very, very beneficial. Now, so what I do is, instead of, when I am accessing RAM, I just bring a block of data. I need one byte, but I don't bring just that byte, I bring a block of byte, and that I need to store somewhere, and that is some storage which is on the chip. So this is why it's called on chip storage. Okay, and that where, so I am bringing k bytes. Now where will I store it here? So I store it in something called the cache memory. Okay, so the cache memory is an intermediate memory which is very close to the CPU, very tightly coupled with the CPU, in the heart of the CPU, right? So, and I can access instructions very, very fast. And what is the role of the cache? It will store whatever is fetched from the RAM, it will store it in the cache. And then, so the subsequent accesses, I need not go to the RAM, but I could keep accessing it from the cache. Are you able to get this? So this is this is how cache memory has come into place. Okay. We will now talk about cache in today's class, and probably next week we will talk more about caches. Okay. Doubt.
Sir, you had said in last semester that keyboard is also a memory mapped I/O.
Yeah, keyboard is also a memory mapped I/O in the sense that the data that comes from the keyboard essentially goes to a buffer in the memory, and then you keep reading it from that buffer.
Then like you told
Yeah, but here is only the control signal goes directly to the CPU. So I am not transferring data, but I am transferring some control. Control C is not a data, right? It's not, you are typing there is a difference between you typing login name versus controls. Yes. So that's the difference. Okay. Right. And you did implement keyboard in your last semester using memory mapped I/O. Right. So you got this. Now we will go into how cache memory is organized. So the difference between virtual memory and cache memory is that in virtual memory I had an elaborate, the purpose of the virtual memory was different, and I had an elaborate page translation mechanism. Now I cannot have another cache translation mechanism here. The purpose of the virtual memory, purpose of paging was to provide you that 4 GB virtual memory. That was the main intent. While we look at caching, the purpose of caching is what? To improve speed of performance, right? This is one purpose. As we proceed, when we go on to task switching, etc., the purpose of cache, I can give you different varieties, colors of purpose of cache. So somebody asks you what is purpose of cache, you can say I am improving performance. That's a good answer, but I will give you excellent answers. Okay, but as we proceed, right? Without cache, your operating system itself will go for a dud. Okay, it will become useless. You cannot even get performance in the operating system. Not just that I could access some memory fast, but there are many more ramifications of that. We will look at it in great detail. But a very simple answer which any Tom, Dick and Harry can give for this is that by having a cache, I will improve performance. Okay, and that answer is sure. Okay, now how is a cache organized? I can't have another page table sitting inside my chip. So it has to be very straightforward. So let us say let me say that there are 0 to 63 locations. So how many bits I need? 6 bits I need. Okay. Suppose I say there are 64 locations in my main memory, and I have say 4 locations in my cache. Right. So how will so what I can do, first I assume I will not look at blocks now. Let me just I am bringing 1 byte. My block size is just 1 byte, just for our initial understanding. Later we will increase it to several bytes. So I need to have a mapping mechanism. So what I do is, this is 6 bits and this is 2 bits. Okay. Let me call this 6 bits as B4, B5, B4, B3, B2, B1, B0. Okay. Now if I bring say a 6 bits, I will store it in location specified by B1, B0. So if I bring 0 from the RAM to the cache, I will store it in 0. If I bring 1, I will store it here, 2 I will store it here, 3 I will store it here. Then 4 I will store in the same location where 0 is. 4, 5, 6, 7, 8, 9, 10, 11. I will do for 12, 13, 14, 15, 16, dot. So 0, 4, 8, 12, 16, okay, 20, 24 and all will be stored in in the 4th location, in the 0th location of the cache. 1, 5, 9, 13, if at all they are brought, they will be stored in this. Then 2, 6, 10, 14 will be stored in the 2nd location and 3rd location. So what is the cache doing? It is actually partitioning your entire address space into 4. One partition has 0, 4, 8, 12, 16, stores these addresses. The other partition stores 1, 5, 9, 13, etc. Other partition stores 2, 6, 10, 14, etc. and 3, 7, 11. So the entire address space of 0 to 63 is now partitioned into 4. So each one of this I call it as a cache line. So I have 4 lines here. In each line, these are the addresses that could be stored. So what I do, I bring 0, let me say this is D0, D1 to D63. So D0 essentially gets stored here. Okay. Now I bring D1, then say I bring D6, D6 gets stored here. Let me say I am accessing data in this way. I get D11, I get stored. Now I bring D4. Then what happens? D0 is erased and D4 is loaded there. Okay, right? You are getting this. So the mapping now is very straightforward. What I should do? I take the 6 bits, I take the last 2 bits, and in that location I go and store this 6 bits. This is the data. So my mapping from RAM to this is just take the last 2 bits and in that location go and store the data you have. Correct? Are you able to follow? So this is a very direct mapping, and yeah, incidentally it is called, this is called a direct mapped cache. Right? Okay. Now what happens here? When initially I was trying to bring, so what will happen? The CPU, when it wants some address, it will generate that address. CPU generates the address, right? Now with this address, it will go to this cache, okay, and see if that address, the data corresponding to that address or instruction corresponding to that address is already stored here. If it is stored here, then it will just access from the cache. Access means read or write. If it is not stored, then it will bring from the RAM and then access it. Right? So what will the CPU store? Generates address, generates the address, then inputs address to the cache memory. If data found, if address stored, address available in cache, that is a better word, then say fetch it, else get from RAM. Okay. So this is what we need to implement. If address available in cache, fetch it, else get from RAM. Address available, if this is true, then we call it as cache hit. If this is false, then we call it as cache miss. We call this as cache hit, another we call it as cache miss. It is not there. Okay. Now, let us quickly get around with 3 or 4 implementation issues in this. What is the number 1 implementation issue? Now we have done paging. What is number 1 implementation issue? In this, generating an address is clean. I will input the address to the cache, that is also clean, because now in this case I'll have to go and find out if address is available in the cache. If this address, the data corresponding, data or instruction corresponding to this address, is it stored in the cache? If it is there, I will fetch it from the cache, otherwise I have to go to memory. Now which location in the cache will I look at? Very easy, I take the last 2 bits and go there. And what is the problem in looking at that?
I don't know which.
Exactly. Now very simple thing, right? I don't know whether it is corresponding to 0 or 4 or 8 or 12 or 16. So what I store here is, in this I am zooming up this location here, what I store there is the actual data plus what we call as tag bits. What is the tag bit? The first 4 bits, the most significant 4 bits, namely B2, B3, B4, B5, I will store it here. Correct? So when I store, say when I store D0, I would have stored 0, 0, 0, 0. While I am storing D4, I will store 0, 0, 0, 1. Because D4 is 0, 0, 0, 1, 0, 0. So when I am generating address 0 and suppose this is stored, I will come, address 0 is what? 0, 0, 0, 0, 0, 0, right? So I take these 2 zeros, I come here, and if the tag bit matches this, if the first 4 bits of what I have generated matches the tag bit, then I know that this is 0 that is being stored here, right? Are you able to follow? Very, very simple, right? Right. Suppose I generate 4, 0, 0, 0, 1, 0, 0, 0, I go to 0, 0, this location, I find the tag bit as 0, 0, 0, 0, but the actual bit I need is 0, 0, 0, 1, then there is a mismatch. Okay. So the first thing is that I will use, so if my address is k bits, I will use some amount of bits to index into the location, and the remaining bits I have to store it as a tag. In this case I had 6-bit address, I used 2 bits to index into the location, the remaining 4 bits I stored it as tag. Okay. Next implementation. Can you tell me what is the next most important issue here?
We'll need a dirty bit.
Dirty bit is next one. Before that, dirty bit is heaven, roof.
Present.
Valid bit, yeah, present bit, right? So, hey, take some clue from what you have learnt, right? This is what you should extrapolate. Any location, no, it will be zeros and ones. So, any data can be valid, right? So, I will have one valid bit here. If it is 1, that means whatever I have stored here is sense. Because when I start, nothing is there. Nothing is there means what? There will be some zeros and ones there. And everything will make sense. Right? I don't have an insensible binary combination. Every value I store, every 0 and 1 pattern I store will make some sense. So I have to, so first I should say that is it a correct valid value which is written by the CPU or fetched from the memory or not. So I will always have a valid bit. So everywhere when you start making these type of storage mechanism, the storage will have some random values to start with. And so there is something called a valid bit. And so if you look at some of our architectures including Intel, there will be a specific invalidate in INVLD, I think, invalidate cache. So you will go and invalidate the entire cache. Means what? You make all the valid bits 0 for all these 4 locations. The next thing which I will finish off in 2 minutes that we have started, we will have again this dirty clean bit business. Why dirty bit is important? Because see, I access D0 to start with. Let us say I am marking it in some orange color. Okay, I started with D0. Now 4 is accessed. Should I write back D0 to RAM and get D4, or I can just overwrite D4? If I write back D0 and get D4 overwritten, then it becomes 2 memory accesses, which is very, very costly for me. If D0 has not changed, that is the value stored in D0 here, value of D0 stored here and here are the same. After I fetch, I am not touching that value, then I need not go and write it back, I can just replace D4. So I have a dirty bit which is set to 1, the moment I go and write something into that location. Okay. So who is maintaining this valid bit, dirty bit, all these mapping, everything is done automatically by the hardware. If you look at what you have done in paging, hey, please finish the paging assignment, then you can enjoy it, cache much more nice, right? Please take some time and finish off that assignment. It's just a jujube simple assignment, okay? Just do it off, right? The point here is that I have, in paging, the entire translation mechanism, everything was done with great support from the operating system. Here operating system will not even know about what is happening inside the cache. Everything is completely handled by the hardware, and it has to be handled by the hardware because on an instruction basis I need this service, right? I can't have an operating system to service, so I cannot have multiple instructions to service an instruction, and that instruction which is servicing has to get serviced. Okay, so there is a recursive problem here. So this has to be handled completely by hardware. Okay, so now what we have stopped off today, I think by Monday we should keep all these things in mind. The structure of a location in a cache. We will have tag bits, you know why we need tag bits. We have the data, which again you know why we need it. Then we have a dirty bit, and then we have a valid bit. Okay, with this we will stop. Monday we will take forward on caches. Okay, but by Monday I request all of you, please spend some time and finish off your paging assignment. Then it becomes easy for you to understand. Paging is very complex. Cache, I assure you, is much less complex. And if you understand paging, then this will be a cakewalk.